So it's now time to begin Carol's talk on nonparametric involutive MCMC. So please go on, Carol.
Cool. Thank you. Well, first of all, thanks you guys for making remote presentation possible today, because I don't think I could actually come if remote presentation is not possible. So today I'm going to talk about the nonparametric involutive MCMC algorithm. This is joint work with Fabian, Zaiser, and Lugon. So the aim of our algorithm is to design MCMC inferences for universal probabilistic programming languages. Universal probabilistic programming languages here just means Turing-complete probabilistic programming languages. And a typical example would be the infinite Gaussian mixture model. And what this is trying to do is that given a data set that is generated from Gaussian mixture, we want to guess the number of Gaussian mixtures in the data set. One probabilistic program that one could write for such a problem is as such, where we sample big K from the normal distribution 3, 1 as the number of Gaussian mixture, or the floor of that as the number of Gaussian mixtures, and then we sample the means of each of these Gaussian mixtures, and then form a mixture model M, and then we observe the data we have from this mixture model M, and finally we return the number of Gaussian mixtures. So this is so-called a non-parametric model, because the dimensions of the means, μs, is not determined. So to design an MCMC inference for such a model, the Markov chain has to switch between states of different dimensions. So what do I mean by that? So this is one state where K, this sample value of K is 2.847, and the sample value for the μs are as such. And we need to figure out, or a Markov chain, MCMC inference, has to figure out the probability to switch from this state to the next state, where K is 3.514. So we have 3 Gaussian mixtures, and we have μs that is of length 3. So we need to switch between states that has different dimensions. And essentially any MCMC inference for an infinite Gaussian mixture model has to in some way solve this problem. How do we switch from one state to another? Right, so now I'm going to just talk about the Metropolis Hasting algorithm and see if it works for infinite Gaussian mixture model. It does not, but it gives us a starting point to see how we can maybe extend it to make it work. So the Metropolis Hasting algorithm, the inputs are pretty simple. We have the target density, which is basically just induced from the probabilistic model. And we set our proposal distribution to be the normal distribution. So a step in Metropolis Hasting, the first step is to sample an auxiliary variable from the proposal distribution. Then the next step, we set x to be v0 and v to be x0. And then we have the acceptance step, where we calculate the acceptance ratio and return x if that ratio is satisfied. So just seeing it in motion, say if x0 is as such, the one that we have before, and then we sample v0 from the normal distributions, and these are the result. The next step, we set x to be equals to V0 and V equals to X0. And we have this. Now, there is a problem here, because if we just go straight to the purple step, well, the acceptance step, the density of X is actually 0, because if we take just X and put it in the infinite Gaussian mixture model, so the sample value for K is 3.514, and then the mu_s is as such. We are actually stuck in the for loop. We need to sample an extra sample from the normal distribution, but we don't have a value for that. And so the density of X is actually 0. So MH would just return X0. And this is obviously not very good, because we want to explore the parameter space. So how can we modify Metropolis Hasting for it to work? So the modified version, we call this Nonparametric MH. And well, besides just changing its name, we add an extra step in between just before the acceptance step. So in this step, which is the yellow step, we check if the proposal sample, which is X or some prefix of it, has positive density. And if it does, then we move on to the acceptance step. But if not, we append the initial state, so X0 and V0 with some samples from the normal distribution. And then we do the kind of swapping again. We suggest another proposal state. And we keep on doing that until the proposal sample X or some of its prefix has positive density. And because we've changed X and the states X and X0, we actually need to do some housekeeping to change the acceptance ratio. It looks a bit crazy, but it's really just some housekeeping. It's not that terrible. So let's look at it in motion again. So say X0 is as such, and then the first step, we sample V0 from the normal distribution, and we get this. And then we take X to be equals to V0 and V equals to X0. So far it's just the same as MH, but now we will move on to the yellow state, where because X has the density of X is 0, we would append X0 and V0 with some sample from the normal distribution. Say these are the samples. Then we would again change X and V to be equals to V0 and X0, like that. Then now we realize that, oh, actually now X has positive density. And so we will return X with some positive density, a positive probability. And if not, we will return X0, and it kind of works. This yellow step here is the crucial part in nonparametric MH. Is the step which takes care of the state movement between dimensions. So in this case, it will be going from dimension 2 to dimension 3. It could also reduce the dimension if we go on to something that has shorter, the prefix has positive density. Okay, so a natural question to ask is, does such an extension actually work for other MCMC inferences? So after looking at other MCMC inferences, we found that there's actually a very nice unified framework to describe MCMC algorithms, which is the involutive MCMC. And this is actually a direct quote. It provides a unified view for many known MCMC algorithms. Here is its pseudocode. What it has as inputs are is the target density at the auxiliary kernel and an involution. An involution is basically just a function where when you applied it twice, you get the identity. So there's 3 steps to involutive MCMC. First step is to sample an auxiliary variable from the auxiliary kernel. The second step is to apply the involution to the initial state, which is x0 and v0, to get a proposal state, v and x. And then after that, we go on to the acceptance step, where we return x with a probability of that. And if not, we return x0. So in the involutive MCMC paper, they have listed 15 that are known MCMC algorithms that are can be formulated in the involutive MCMC framework or some combinations of involutive MCMC samplers. And well, which in particular, Metropolis Hasting is also can be formulated using the involutive MCMC framework. And in this case, we take the auxiliary kernel K to be the normal distribution and the involution to be a swap. Of course, if you swap something twice, you get back the same thing. So that's an involution. Right. Oops. Oh, okay. There we go. So now the second question is, what are the assumptions for involutive MCMC for such an extension to work? So to look at that, we have found 3 assumptions that that various inputs have to satisfy. So first one, for the density, for the target density, we have assumed that it comes from a probabilistic program. So that density has to be integrable and almost surely terminating. And also we need an auxiliary kernel for each dimension. And so for each natural number, we need an auxiliary kernel. And similarly, we need an involution for each dimension. In particular, it has to satisfy this A3 property, which means that for every state, if we crop it and then apply an involution, we would get the same result of that from just applying the involution and then crop it, given that we don't kind of crop those things too much. So that is the third. I can talk a little bit more about the third assumptions if we want to, but that's kind of it. So out of the 15 algorithms that is listed as and can be formulated using involutive MCMC, we found that 8 of them can be extended to using this method for non-parametric models. But there are a few that does not. And we have listed some reasons why it couldn't do it. For Neutra, ANICE-MC, and Learn-to-HMC, it's because they required learning in their involution. And it gives an irregular involution and may or may not satisfy A3 because it's learned. We don't know. And for Gibbs and multiple try Metropolis, it's because the auxiliary kernel depends on the target density, which is transdimensional already, so it doesn't work. And for reversible jump MCMC and non-reversible jump MCMC, the involution is already transdimensional, so we can't do it. Right. So this is the pseudocode for nonparametric involutive MCMC. I hope that you can kind of see that it's very similar to involutive MCMC. It's really just adding an extra step, the yellow step, where we kind of deal with the state movement between dimensions. So we have done some preliminary experiment on these extensions, and we look into the infinite Gaussian mixture model with 30 data points, and which is derived from 3 Gaussian distributions. So basically, in the histogram, the correct answer should be 3, and we can see that the NP lifted MH actually works best in this regard, and the other works kind of relatively okay. SMC is our kind of baseline, so it kind of works okay, but obviously more experiments need to be done to see how it performs. So as a summary, NP-iMCMC is a framework for designing MCMC inferences for universal PPLs. It automatically takes care of the state movement between dimensions, and so we don't need to design by hand when and how to jump between the dimensions. We also have an invariance and convergence result for NP-iMCMC with the invariance. We've listed the assumptions for the invariance result, but for the convergence result, we need a little more assumptions. Right, yes. So basically, NP-iMCMC is telling how we can switch from one state to another. Yeah, some future work. I think it would be really interesting to look into correspondence between traces. So we can see that in the yellow step. We just add samples. We append samples from behind, but what happens if we do it in the middle, or like other smarter ways or more clever way of actually adding samples or extending the dimensions? I think that would be quite interesting to look into. And of course, we need to do more experiments on NP-iMCMC. So I think that's all I want to say for today. Thanks for your attention.
Thank you very much, Carol, for your talk. We have time for a very short question before the beginning of next talk by Fabian. So if there is someone who wants to ask a question.
I have a very quick one if no one else has.
Yes, go on, one.
So just kind of zooming out very far, can you give an intuition as to when this will be a really good thing to apply, and what kind of examples this inference algorithm is just going to hopelessly trip up and not work? You know, if I have to choose an inference algorithm, why should I reach out for one of these, and when should I just avoid it at all costs?
I'm actually not too sure. I think it's more about whether or not you want to, if you want to kind of customize your like jumping of dimension in your MCMC algorithm. If you don't want to do that, and you just want to kind of have an easy design in your transdimensional sampler, then I guess this would be quite a good choice. But I think if you want to custom-made your sampler, it's probably going to perform better because it's custom-made. So I guess it's just kind of a it might be suitable for some use case and might not be for others. But yeah, I'm not entirely sure.
Okay, thanks. It's a difficult question, but I just wanted your intuition, and you gave me that, so thank you. And thanks for the talk.
Thank you very much, Carol, for your talk.